Welcome back to My Favorite Universe. In this particular lecture, we're going to review things that can bring an end to Earth. Titled this one, Ends of the World. Now, typical references to the end of the world that you might hear, people might think of a rampant virus that totally decimates an entire species. If not some other species, then perhaps humans themselves. There's a lot of talk about, especially in the days of the Cold War, about global thermonuclear exchange, bringing an end to Earth. Or perhaps just the extent to which we are destroying the environment. That's often how you think of people talk about the end of the world. But these Save the Earth slogans are really, they don't mean save the Earth. That's not what they mean. Earth is going to be here no matter what we do. Earth, the planet. It's actually egocentric to say, let's save Earth, when in fact you're only really talking about saving Homo sapiens. Earth was here before us, it's here now, it's going to be here long after we are gone, in a memory in the fossil record. So what I want to talk about are real scenarios that put the entire planet in jeopardy. I can think of three scenarios for this lecture. One of them, well, all of them actually, we actually won't live long enough to see. So then why am I talking about it? Well, because the formulations of astrophysics allow me to tell you about them. So why not? Maybe if our species lives long enough, our very distant descendants will care about what these prognostications are. But the laws of physics and the phenomenon in the cosmos tell us what is going to happen in the very distant future. And let's start off with the death of the sun. Following the death of the sun, we'll get to the collision between our Milky Way galaxy and our nearest neighbor, the Andromeda galaxy. And the third of these will be the heat death of the cosmos. Let's start with the sun. We know what the sun is made of, okay? Made of gas, hydrogen, and helium mostly, and some residual of other materials. That's fine. But what we have are the colleagues of mine who specialize in stellar evolution. You give them the birth ingredients of a star, and they crank it through a machine, and they look through the forces and the thermonuclear interactions and the whole life cycle of a star. And what they do is produce, I'm going to call them this, but they produce what are basically actuarial tables for the stars. This one is this old, and it's going to last for another this many years, and it's got this kind of health, and the black hole is a little too close to it, it's going to have an early death. They figure this stuff out. So let's look at the actuarial statements for the sun. The sun was born about 5 billion years ago, giving birth not only to itself, but to the entire solar system. We date Earth back to about 4.6 billion years. The sun is going to live another 5 billion years. So we're exactly midway. We're middle-aged. We now, I'm referring to the sun. How about the sun's structure? Well, let's look inside. Starting at the sun's surface, here's a nice image of the sun, reminding you that it's a hot and turbulent place. Strong magnetic fields embedded in the plasma that is the outer surface. These magnetic fields grab onto the structure of the sun, and they snap and twist, and pieces of the sun burst forth. It is a busy place. It's a busy place. On the surface, it's about 6,000 degrees Kelvin. In the core, about 15 million. It's hotter as you get towards the center, as you might expect. In the center is the source of all the energy generated within the sun. We call it the core. And in the core is where the thermonuclear fusion takes place. It is stable. It is in equilibrium. Hydrogen atoms, the nuclei, are being brought together to make heavier nuclei. You take 4 hydrogen atoms, and what do you get at the end of that? You get helium. We go from hydrogen to helium. And the act of doing that releases energy, because the act of doing that loses mass. And we use the E equals mc squared equation of Einstein, our first equation any of us ever learned, even before we know what it means. That equation applies to the center of the sun. That energy is being generated, and it's got to get out. It's trying to get out. The sun, by the way, wants to collapse under its own force of gravity. But it has a hard time doing it because this energy is working its way out. And the balance of forces and pressures between the thermal energy caused by this thermonuclear fusion and the gravitational pressures trying to collapse the star are in balance. So the sun basically keeps its same shape and the same rate of energy output for billions of years. It's a very efficient process. By the way, before we knew that it was thermonuclear fusion going on in the center of the sun, people postulated that it might be a lump of coal in the center. That was back in the 19th century, when coal was what produced energy in your homes. It was fascinating to bring your sort of home life into the cosmos on the assumption that it's just a big charcoal briquette out there in the center of the solar system. But this party's not going to last forever. Eventually, the conversion of hydrogen into helium, that can only continue while there is hydrogen in the core of the sun at these temperatures. One day, the sun is going to run out of hydrogen in the core. By the way, you need these high temperatures for a very simple reason. The nucleus of a hydrogen atom is a single proton. The nucleus of any hydrogen atom is a single proton. And I just told you that we're bringing together these protons to create a brand new nucleus, to create a helium nucleus. Well, how am I supposed to bring two protons together when they have the same charge, a plus charge? And plus, as you know, like charges repel. So here are these protons. I try to slam them together, they repel. Try to slam them, they repel. And the only way you can get them to actually touch is if you create a high enough temperature so that their speeds overcome that repulsion. In high temperature gases, particles are moving very fast. And so they overcome. It's like rolling something up a hill and then it rolls back. And you say, let me roll it a little faster. Almost gets to the top and then rolls back. Well, now you really shove it, and it goes all the way up to the top, over the cliff, and over down the other side. That barrier has to be overcome, and it's overcome by the high temperatures in the center of the star. So they link together. At the moment they touch, a brand new force takes over. It's got to be a strong force to keep two protons together. In fact, it is a strong force. We call it the strong force of nature. You don't have much encounter with that in everyday life, but it's there, and it's operating in the center of the sun. So we run out of hydrogen. Now we've got a big blob of helium in the center of the sun. What do you do with the helium? Let's try to fuse it into yet a heavier element. Can't fuse helium at 15 million degrees. No good. It's not hot enough. Why? Because helium has two protons. You're trying to bring two protons together against two other protons? That has even more repulsion. You need an even higher temperature. So, if we had a knob, we'd just say, okay, turn up the knob. Let's get to the next temperature, the next magic temperature to fuse helium. Well, the sun actually has a built-in mechanism to do that. It's called the loss of equilibrium. And in that loss of equilibrium, the energy snuffs out, no more hydrogen. There's nothing to support the star. What does the star do? It collapses under its own weight. And the act of collapsing heats the center of the star. It's marvelous. Marvelous regulatory system inside of these stars. It heats it until it collapses and heats down in the core until it ignites helium. What temperature is that? About 100 million degrees in the core. Much hotter than what it took to fuse hydrogen to helium. So helium, you look through the nuclear pathways, and in the end you end up taking 3 helium nuclei together and making the nucleus of 1 carbon atom. And that releases energy. Oh, but it releases a lot of energy. Much more energy than hydrogen going to helium in total. How do you get that energy out? the star has to respond somehow. Energy's trying to get out. You know what the star does? It begins to expand and expand and expand. That's going to happen to the sun. 5 billion years from now, it's going to run out of hydrogen. It's going to start fusing helium into carbon after it collapsed a little bit, got the temperature up, and started cranking out the energy. And it's going to start doing that. It's going to swell, and you're going to look in the sky and say, sun is getting kind of large. And as it gets large, the outer surface cools. It becomes cooler. Astrophysically, when I say something's cool, it's thousands of degrees still. The surface of the sun will drop from 6,000 degrees down to about 2,000 degrees. Start glowing red. And become enormous. How big? It'll first fill the entire orbit of Mercury, the closest planet to the sun. It'll engulf Mercury and then fill the orbit of Venus. It'll engulf Venus and begin to, what's next? Mercury, Venus, Earth. It'll engulf Venus and then fill the orbit of Earth. Imagine what that looks like. Just imagine. Imagine what would sunrise be? It would be the whole horizon just rising up. Eventually, if it engulfs the entire orbit of Earth, the sun occupies half the sky. Half the sky. Here we have an artist rendition of the scenario depicting a red giant about to engulf its next victim. In this case, an attempt has been given to show Earth and how the temperature of the surface of the Earth might be on the rise. Of course, as I described, the temperature of the sun's surface is dropping. Yes, it's dropping from 6,000 down to 2,000 or 3,000 degrees. But as that surface gets closer to Earth, the radiant energy that's hitting Earth goes up. And eventually the temperature of the Earth becomes the same as the temperature of the sun's surface because we're orbiting on the surface. That, once again, would be bad because at 3,000 degrees, what begins to happen? Well, you heat the oceans, bring them to a rolling boil, and they evaporate into the atmosphere. The atmosphere itself gets so hot, you evaporate it, laying bare Earth's surface without protection, without any way to cool itself. Now, the surface starts rising in temperature. You vaporize all known life. Render rocks aglow, like what goes on inside of a volcano. Then, of course, Earth, as we get engulfed, Earth slams into the gas that is the material of the sun. That's bad for the orbit. The orbit was happy out there in its near vacuum with nothing to force a decay in its motion. And now we've got star material there. It plows through it, slows down its orbit, and it descends, spirals down in, and evaporates into a puff of smoke. That'll happen in about 5 billion years. The end of the Earth. End of the Earth. I once wrote a planetarium show that depicted just that scenario up on the dome, the sun getting larger and had sort of ominous music. And unlike anything else I've ever written for that audience, wrote about big bangs, meteor impacts, all kinds of bad stuff I've written about, the sun getting bigger in the sky. I got mail for years from parents who told me their kids could not get to sleep, or they woke up with nightmares because they were worried that that was going to happen next week or in their lifetime. And so maybe there's just something scary about that notion that something we've taken for granted, the stable sun, would somehow be responsible for our own demise. Not only the demise of life on Earth, but of course of the entire planet. So this red giant phase of the sun, it actually continues. Eventually runs out of helium. There's a core of carbon left over. Well, now we want to fuse carbon. How do you do that? Will 100 million degrees do that? No. No, you need a higher temperature. Well, let's try it. Here we are. We're the sun. We now got this core of carbon, and now we have no energy source. So we've been there before. What happens? The interiors of the sun begins to collapse. Temperature begins to rise. Not enough mass to raise the core temperature up to the next magic place on the thermometer where you can begin to fuse carbon. We don't have enough mass to get there. So the sun stops with a core of carbon. And these outer layers had gotten so far away from the sun that they were only then tenuously connected to what was formerly their home. And eventually, it dissipates out into space. And it makes, in fact, a rather beautiful view when viewed in other solar systems. In fact, we have pictures of such objects. We call them planetary nebulae, not because it has much to do with planets, because it's really just part of the life cycle of a star. It's just because William Herschel, when he first saw these in the sky, he discovered them with his telescope. This is now a few hundred years ago. He discovered these with his telescope, and they look like disks on the sky, just like the way planets looked. Stars are just points of light. Planets, you can see the full surface of a planet. And these planetary nebulae were so circular that he said they resembled planets. He called them planetary nebulae. But there's nothing deep about it. It's really a misnomer, and it's stuck. Notice the core of the star that has been laid bare. That in the center is what we call a white dwarf. No bigger than the size of the Earth. And it's dead nuclear material. And the rest of that is the outermost layers of the red giant. And by the way, if you wanted the extent of the solar system, this is now so large, the full extent of our solar system only comes out just the tiniest bit from that central point of light. So by the time it's a full-blown planetary nebula, it is enormous. Many, 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 many times larger than the full extent of the solar system. And there are thousands of these in the night sky, and they're gorgeous. You can make whole catalogs of them. Here's another one, NGC 6751, another planetary nebula. Look at that. Looks almost explosive, although it did happen rather gracefully. In the center there is what we call the white dwarf. It's either composed entirely of helium, or in our case, it'll be composed of carbon. And any solar system, any system of planets that this once had, they are kissing their days goodbye. If we are on Earth, and that begins to happen to the sun, that kind of makes interstellar space travel a high priority, doesn't it? And while the sun is on its way out, we at least want to be able to travel between planets. Let's go out to Mars, okay, as the sun is coming over our back. Maybe Mars will be nice and warm like Earth. And then it starts to come out closer to Mars. Maybe let's find an asteroid to hang out on, or one of the moons of Jupiter. But we've got to be able to do something. Can't just sit here like a chicken in a pot, ready to get cooked. Let's go on to the Milky Way. The Milky Way, that's our galaxy. It's going to have problems of its own. But these are kind of fun problems. The Milky Way, this is not a picture of the Milky Way. It's a Milky Way look-alike. I can't step out of our galaxy and look back, take the snapshot, and go back in and show that to you. This is a look-alike. We've got a little nuclear bulge in the center. We have a spiral shape. And if you saw this edge on, it would be quite flat. Milky Way look-alike. It's one of the countless galaxies in our night sky. Just to give you a sense of what we look like. That system is actually the blurred, fuzzy light of 100 billion stars. Back in the 1920s, Edwin Hubble, famous American astronomer after whom the Hubble Space Telescope is named, he looked around the night sky, found all the galaxies, did a little Doppler measurement on them, slightly different from, but similar to in principle what a police radar gun does when it gets your speed of your car on the street. He looked up at all the galaxies in the sky and said, how fast are they moving? They're coming towards us, coming away, and he made a whole catalog with the help of others. And once he made that catalog, he found out that nearly every galaxy was moving away from us. That was the discovery of the expanding universe. Some galaxies, however, were coming towards us. We had motion towards each other. And one of those galaxies is the Andromeda Galaxy, the nearest galaxy to our own. And it's not surprising, if all galaxies have random motions, and the expansion of the universe becomes more and more significant the farther out you get, then you might expect the nearest galaxies, with whatever is their speed, to be overcoming the expansion of the universe. And in fact, that's just what's happening. These random motions have overcome whatever is the expansion of the cosmos in the nearby universe. And we are on our way towards each other at a speed about 100 kilometers a second. What's that in ordinary terms? About 250,000 miles an hour. 250,000 miles an hour. Fast. Here we have the image of Andromeda, the closest large galaxy to our own. It's about 2.4 million light years away. Beautiful. And by the way, it has a satellite galaxy. You see the little smudges off below and above it? Those are satellite galaxies in its vicinity, orbiting with the rest of the 300 billion stars that are in it. Well, take a close look, because that is the place we are headed. Strictly speaking, we are approaching each other, and the closing rate is 250,000 miles an hour. Collision is imminent, assuming that we don't have too much sideways motion. It's possible that we have sideways motion that we haven't measured yet that'll take us an orbit around it. But the evidence thus far suggests that, in fact, we are on a plunge orbit right on down to the center. Two galaxies colliding, and Andromeda is 2 or 3 times the mass of the Milky Way. It's going to be a bad day for the structure of the Milky Way galaxy. When will that happen? Well, it's 2.4 million light years away, and a light year is the distance light travels in 1 year. It's a distance. It's about 5.8 trillion miles, if you want to know that sort of thing. 5.8 trillion miles in a year. That's a light year. And it's 2.4 million of those away. That sounds far, but we're gonna close that gap, and it'll take between 5 and 7 billion years to do it. So, if we survive the death of the sun by whatever means, we'll be around to see the collision between Andromeda and the Milky Way. Now, we have computer simulations that tell us what this will do. We have a very strong idea of what happens. The galaxies feel tidal forces between each other, where one side of the galaxy is closer than the other, so it feels a stronger force of gravity, and it gets tugged and twisted and turned. Thing looks like a train wreck when it's done. And we didn't make this up. We do the calculation, hey, this looks like a mess. Then we look out in the cosmos, and we find galaxies that are in the middle of collision. By the way, a collision takes several 100 million years to execute. So we're not sitting there eating our sandwich watching a collision happen. But when you do, there are enough galaxies out there. You can see some that are like this far, and then that far, and another set that's that, and another that's intersecting, and another that are all distorted already. You've got a whole, the universe is big enough so that you find pairs of galaxies in every stage of collision. And in that way, we can test our models to see, well, were these galaxies born looking like that, or is there some story that's unfolding? And in fact, you compare all these pictures to our models, and that is what it looked like at stage 1, stage 2, stage 3. We've got the whole evolution of the collision mapped out. It'll happen in 5 to 7 billion years. So what actually goes on? Well, space is pretty empty. We've got big gas clouds. When gas clouds collide, they'll stick like hot marshmallows, and it'll give birth to new generations of stars. That's fine. Stars, however, are so separated that as many stars as are coming into this encounter, they're not going to hit each other. Statistically, they're just not going to hit. So that's not going to be a problem. We can sit back and watch. What I worry about, though, is a star that comes kind of close, not hitting the sun, but close enough so that maybe we, Earth, lose our gravitational allegiance. Here I am happily orbiting the sun, and then another star comes closer to me than the sun is. What then? Well, I'll start to respond and react to that force of gravity. In fact, I could be stolen from the sun, kind of like a flyby looting. Worse yet, but if that's the case, fine. Now I have a new home star, but maybe I'm not at the right distance. Maybe I end up in orbit too close and all my water evaporates. Maybe I'm in orbit too far and all the water freezes. Well, we want liquid water for life as we know it. So that's not going to be a good thing. It's probably going to be bad for us. But at least we'll have a home star. In another scenario, Earth or any other planet could get flung out from both stars. And we become quite the contrary to the sun becoming a red giant. What happens? The oceans freeze. The atmosphere liquefies. And all life as we know it ceases, except, wait a minute, there's still some energy. There might be some geothermal energy sources deep down in the Earth's crust. We've got that now, we know. We have life forms that thrive on geochemical energy that have nothing to do with the sun. It may be that there are thousands of interstellar planets that have life thriving beneath its frozen surface, existing on the energy sources left over from the formation of the planet in the first place. While this image is a real photo of two galaxies in real collision, we can also display this as an artist would show it. And in this particular case is given to show how the distortion of the spiral arms can make for some rather graphic displays. And this is very early in the collision. A few more of those passes, you have a wholly unrecognizable train wreck. By the way, how cold do we get if we're flung out of E8? All of whatever heat we had into space, becoming this little ice cube. So that's a bad day for Earth. You hope that no star comes that close. But perhaps the most terrifying of all of these deaths is the heat death of the universe. The Big Bang is the most successful theory of the universe ever put forth, and it describes an expanding universe, expanding against the will of gravity that would try to have it collapse back, because we don't have enough gravity to accomplish that. We also know that there's this new pressure that was discovered. We call it dark energy. That's the accelerating universe. We know that the universe not only doesn't have enough mass to bring it back, there's a force that will make sure that never happens. It's the accelerating universe. So we're on a one-way trip. As the universe gets bigger, its temperature drops. When we were 1/1000th our present size, the universe was about 3,000 degrees. Today it's 3 degrees. When the universe gets 1,000 times bigger than it is today, then it's 1,000th of 3 degrees. That's cold. In the distant future, what happens? All the gas clouds run out because they've made all the stars they can with their supplies. And all the stars burn out. So we start running out of our supply, we run out of stars, and galaxies start to turn off one by one. And the night sky goes dark. And the galaxies that are in our night sky now, whether or not they turn dark, the acceleration of the cosmos will move them so fast that they'll go beyond the visible edge of our horizon. They will be redshifted out of our view. Not only that, all processes in the cosmos, anything that relies on energy moving from one place to another, and machines do that. Volcanoes is energy from down here coming up. Earthquakes is energy builds up and releases. All the movement of energy will cease. What could happen in the universe ceases. The universe is cooling like a pie out on a windowsill, radiating its heat out to the cool air. Bad day for the universe. When that happens, we can assert that the universe, though born with a big bang, has died. Not with a bang, but with a whimper.